Hi everyone, and welcome to this session. We're very excited to talk to you about the deep learning pipelines, which is a work we have been doing in collaboration with a few other colleagues at Databricks, and which aim really at helping out people like everybody here in this audience to use deep learning at scale and in a simple manner. So just to give you a little bit of background, you most probably heard Suwan's amazing demonstration this morning. She hails from Carnegie Mellon, and she has been working with me on deep learning at Databricks. As for me, I was a very early user of Spark during my PhD at UC Berkeley. I think I was user number 2 or 3 of Spark. Back then, it was really buggy. And of course, deep learning was not something that was being considered back then. So this talk here is about really how trying to move the deep learning from all the complexity that it has to something that can be used more into production. So we'll talk a bit about what is the current state of deep learning at scale and with Spark. And this will lead us to explain why we wanted to have yet another library for doing deep learning with Spark. And this talk really aims at being practical. So we want to share with you how you can use this library for most of the common tasks that you would want to do in the context of data science or data engineering. And finally, of course, this work is never complete. And there's a lot of things that we would like to do. And also, I hope that the discussion we'll have at the end will also help us steer the direction for that. So I don't think we'll take questions at the. So this is, by the way, this is a long talk. This is a deep dive. So I don't think we'll take questions for the first at the end of the first half hour. However, we'll reserve more time at the end of the second session so that we can have a deeper discussions. So what is the so these days when people want to use deep learning, there's really a lot of options, and there's really no satisfying option for doing deep learning with Spark and at scale. So just to make sure that everybody is on the same page here, what do we mean by deep learning? So you can find a lot of definitions, but really I think the one that is the most practical and the most intuitive to think about is that you can think of deep learning as being a way to express very complex transforms in a way that is essentially layered. And within these layers, you can have very different functions for doing activation or transformation, but it's really the structure that with multiple layers, usually more than 2, and some people go into the hundreds of thousands of layers. And really the structure is at the core of all the algorithms that power deep learning these days. So what is it being used for? There's a lot of use cases. So you can use them now for doing classification, regression, and also more arbitrary mapping. So you can really use it as a function that takes some arbitrary data on one side and transform it into some other kind of feature vectors. So of course, a lot of people, so a lot of these techniques are not new. Back in the 80s, these kind of data structures and transforms were mostly known as neural networks because it was really inspired by how the brain and especially the visual cortex is organized. And so they were not so much in favor in the 90s, but they came back in the 2000s and very recently, mostly because the computers are much more powerful these days. The data that we collect also is much larger, and that makes these that makes these techniques much more powerful and much more effective, especially when you have very large data sets. And finally, there has been also a lot of progress on the algorithms that we used for training these complex data structures, because at the core of these training algorithms is always the idea of doing some sort of gradient descent, and that we'll talk more about it later. But now there has been much more understanding about how these algorithms work and how to make them effectively train some very deep and nested networks. So we all know from reading the news how successful deep learning has been. And for example, recently we had the example of AlphaGo, which now is the undefeated champion in the game of Go. But These days, for nearly any of the cell phone that you have, it is being used for doing complex image processing, such as image interpretation, image classification, and also when you use most of the tools, even for in self-driving cars, or even in, when you talk to all the devices around you, it is doing for you a lot of automatic translation and interpretation and speech recognition. So it is really now becoming a pervasive technology. But in order to reach this kind of success, you really require a lot of effort. So there are multiple reasons for that. So one of them is that deep learning, even though it is an established engineering discipline at this point, it still requires a lot of tweaking and tuning, and there is no exact science to explain really how it works and how you can achieve good results in any situation. And also, because you need to try out a lot of configuration and combination, it requires a lot of prior knowledge about how it works on a particular problem, and also simply a lot of engineer hours to simply try out a number of things and see what eventually works. And this is not helped by the state of the libraries that people use to express deep learning. Because these libraries tend to have a fairly low-level API. They really work at the level of expressing mathematical transforms. And they're also not integrated with the tool that we're used to in practice. For example, if you use all the industrial technologies, such as the Amazon cloud, it is hard to move data from the environments in your enterprise into some of these deep learning frameworks. And also distributing computations, if you want to accelerate things, is really hard to do. And usually it is done by the largest companies that have been able to master these technologies for a number of years now. So we would like to accelerate that, and also would like to be able to see how Spark can help in that respect. So if you look at what Spark offers in this context, there is actually very little inside Spark itself. All you have in all these, for all the configuration and all the kind of networks that you can describe, the only one that you have is the multi-layer perceptron, which is fairly limited. And nowadays you have much better architectures that are being used, which are not available in Spark. So this is why you have a lot of Spark packages that try to add this deep learning capability to Spark. So essentially it falls into two categories. Either people start from an existing deep learning framework, and then they build a Spark wrapper around it, or they directly build libraries using the Spark primitives for doing the communication, the data ingests, and so on. And so I will not go through all the list here of existing libraries, because this list is never exhaustive. I think 2 weeks ago I learned about a new one, for example. So this is always rapidly evolving here. And also, if you look at what is being done in the industry, and also the fact that there are so many libraries really shows that there is limited adoption in practice for doing deep learning in production. But there is clearly a huge potential, because a lot of the industries, a lot of the companies around us accumulate a lot of complex data that is really easy to use, and that is really well suited for deep learning, as all the big tech giants have shown us. So the question really is how we can accelerate this transition from being something that is being used only in research and in the largest company that can afford that, to the rest of us.
Okay, so yeah, that's why we built deep learning pipelines. As the demo this morning tried to show, it really focuses on deep learning with simplicity. This is an open source Databricks library, which means it's open source, but we authored it in the beginning. And again, it focuses on ease of use and integration. So instead of having its own computational backend, like TensorFlow and Torch, like all of these are different ones, it integrates with them, but without sacrificing performance by integrating with Spark nicely. And currently, the primary language is Python, but we're adding support for Scala for some of the features in there. And we'll probably see which ones actually make sense in Scala and which ones don't throughout the talk. Yeah, the two core principles are using Spark for scaling out the common tasks and integrating with MLlib pipelines to get that concise workflow that we saw earlier. And to talk about what's in this library, it's useful to look at a typical deep learning workflow, which is very much like any other machine learning workflow. So the first thing would be to load the data, right? I think in deep learning, it can be more challenging because you have more complex data, like images and time series and so on. And then you would probably do some interactive work to see what kinds of things are in your data set. And then you might start training a model. In the deep learning case, it probably involves selecting some sort of architecture for your neural network, and then optimizing the weights with some hyperparameters. And then you evaluate the results, potentially probably retrain in the case of deep learning, using either a different network architecture or different hyperparameters and so on. And finally, you would apply that model once you're happy with it to a test set or a production data set. Right? So in deep learning pipelines, we have a bunch of tools for each of these steps. For example, for loading data, we added support for image loading, since that was not well supported in Spark. For interactive work, we'll talk about some of the canned pre-trained models you can use and how. For training, we'll talk about transfer learning, as well as how you can do distributed tuning with it. And for application of the models, we'll talk about batch prediction, as well as deploying it into SQL for use. Probably with the time, we thought we would do part 1 up to transfer learning, but we'll see. Okay. So we'll talk about the parts now.
Sure. So yeah, so let's go now a bit more into details for each of these parts and see how we can use Spark with the help of deep learning pipelines to distribute them and make them more efficient. So let's talk first about the loading data. So Spark already handles numerical vectors and the complex structures and like anything you can express in SQL. But so far, it hasn't had support for other kind of data sets, such as images, which is really prevalent in the context of deep learning. So this is why deep learning pipeline has an interface for loading images. And for example, here, if you use this read images function in Python, then you can point to any directory on HDFS or S3, and it will load all the images in a lazy manner inside the data frame. So if you look at the content after that, each of the images then is loaded as a set of pixels, along with other extra information that then can be used by the deep learning libraries or other image processing libraries. And so in that respect, we have, so this library also includes some facilities to express and manipulate images. And it is based around a schema for describing images around inside Spark and describing how they can be transformed. So it contains most of what you would expect from an image perspective. So support for arbitrary kind of images, such as RGB, BGR, alpha channels, and so on. And also, from the perspective of users, you can load these images back and forth with PIL, so the image libraries inside the Python. And so for the sake of this talk today, most of what we're going to describe works with these images, or also can work with other data types supported directly by Spark. And also, I'm happy to announce that in collaboration with Microsoft, we're going to incorporate this image support directly inside Spark. So then you won't need an extra plugin to load images inside Spark. And we hope that we're targeting the support for Spark 2.3. So this way, you will have inside Spark the basic facilities to load images and to express them inside data frames. And already, we see a couple of libraries which rely on this schema so that you can do, for example, OpenCV-based transformations on these images or deep learning transformations. So now let's look a bit at at how you can do interactive work with now that you have loaded these images. So you can do a lot of, so one of the most typical way of using deep learning, and the one the easiest to get started with, is if you take some existing models that have been already pre-trained, and we would like to make them and also make them available inside more complex machine learning pipelines. So we won't go now into how it is expressed directly within MLlib, so the machine learning component of Spark. But really, all you need to know is if you want to load an existing model, for example, Inception from Google, all you need to do is load this predictor, point which of the columns in the data frame contains the image input, point the output of this model. So for example, in this case, it is going to be predictions with labels corresponding to different categories. So essentially, it's going to tell you what the image contains. And you can then call this transform function that will apply this deep learning model and output the set of categories. So for example, if you apply it on some flowers, then it is going to give you a number of classes and along with probabilities. And for example, here it would recognize correctly that this is the image of a daisy. So this is great for getting started. But then, of course, we want to be able to move beyond that and to train some new models based on these first experiments. And Tuan will talk about the training.
OK. Oh, part of training. Yeah, so we're going to talk about two ways to use deep learning pipelines for training. One is going to be transfer learning, and we'll also talk about hyperparameter tuning probably after the break. So we can start with transfer learning. So the using of that pre-trained model on your data is great if you have the exact same problem, right? If you want to identify cars, for example, you can probably just use one of these ImageNet trained models. But in most people's cases, that's not true. But at the same time, if you want to train a model from scratch, I think we talked about this many times today, it takes really a lot of time and effort to do so. And transfer learning is kind of in the middle that leverages that learned representation in these networks to train a model much faster. And briefly, it goes like this. So this is an example of a supervised learning model, right? It's got lots of layers. And then there's a softmax layer at the end that essentially gives you this probability distribution over the labels that you could have. And these intermediate layers, they capture things like edges and textures and shapes and so on. So then we can take away that layer that gives you the labels and instead use the output from one of these intermediate layers. And then from there, we can stick on another classifier on top of it, which will be a much lighter weight classifier than having to train the entire model from beginning to end. And then use labels for, let's say, another task that might be, are these roses or daisies with labels, but a lot less training data than you would have had to if you had to train this whole model from scratch. So that's the idea. And to talk about how this is implemented or provided in deep learning pipelines, we need a little bit of an MLlib pipelines primer. So MLlib, for those who are not familiar with it, is the machine learning library inside of Spark, included in Spark. And there are two core concepts here. One is transformer, and the other is estimator. So a transformer takes in a Spark data frame and then returns another Spark data frame with the original columns plus new columns that contain the transformed data with the computation that this transformer is supposed to do. Estimator, on the other hand, is like a learning algorithm. For example, logistic regression is an estimator. And these objects implement the fit function, which produces a model. And a model is really a transformer because it's going to take features, most likely, and output a set of labels or probabilities. And then when you string a bunch of, and other popular transformers are actually feature transformers. So things like one-hot encoder and those things are all transformers. So you can imagine you can string a bunch of these, and then what we get is a pipeline. So these concepts are pretty similar to what's in scikit-learn and so on, but MLlib provides this API with distributed computation. Right? So if we go back to the transfer learning example, for example, deep learning pipelines provides a transformer called deep image featurizer, which takes care of this layer that takes an image and then outputs a representation that's good for the image. And to write this, to think of this as a pipeline, you would have these different steps strung together. And in code, it might look something like this. You have a deep image featurizer object that you specify with the model name. And then you also specify a classifier like logistic regression. And then you can put that in a pipeline as featurizer and then logistic regression. And if you do a fit, this will output a model that you can actually export and use. Actually, you can't export the featurizer yet. We're fixing that persistence issue. OK. But, and then it will apply that deep learning transform and then the learned logistic model classifier if you use it on new data. So transfer learning in this sort of workflow is usually for classification tasks. So you want to go from the original task for which the model is already trained on lots of data. It's great. And you want to go to a similar task in a slightly new domain. This is great. But I would say other forms of leveraging this learned representation can be loosely considered transfer learning, like finding similar shoes. And in that case, right, we're essentially replacing the logistic regressions part here with other algorithms. And those could be similarity-based algorithms, anywhere from nearest neighbor. We actually did LSH this morning, right? And MLlib also has a non-approximate k-nearest neighbor algorithm as well. You could apply clustering to see whether you can get some meaningful groupings of the images. And use any sort of distance computation for things like anomaly detection or duplicate detection, recommendation we saw, or even search result diversification is a customer use case we've seen from here. We could take a break. Yeah, we should probably take a break because the next section is kind of long. All right, thanks.